session. We have 13, right? So after this class, we have 2 more classes. We have one next week, Monday, and then the last one we will actually have on Friday, the 25th, because the Monday of that scheduled class is Easter Monday, right? So that's going to be another rescheduled class. So we had 3 rescheduled classes this semester, right? But that's okay. It's just a few more classes and then the final exams. Today I posted a number of things on Canvas. You all had a chance to review it yet. One of the things I posted is the second assignment. So that is assigned today, and I'll give you about a week to do that. Okay, we will go through the assignment in more detail later on, right? And I also posted notes and formula sheet, right? The reason why I posted that bit of information is because that data will be in your examination in the question paper, right? It will be to the end of the question paper. It is quite a number of pages, right? It's 9 pages. So I just want you all to be familiar with it so you don't be too overwhelmed when you see it on the day of the exam. So we'll go through that also in class, right? And I'll just sort of highlight some of the things. But you have been using that information throughout the class, okay, for the Laplace and Z transforms and the Fourier transforms, right? So, I mean, you know the information, but maybe not in the format we have been presenting it in class so far, right? So what I would really advise you all do is to just have a look at the notes and formula sheet and just be familiar with it so you know where to get the information we use more frequently, right? As opposed to the entire sheet itself. Okay, right. And what we'll do today, we'll have a class today where we will first go through some signal characteristics. We did go through it before on the first class, but I just wanted to give you all some more examples and I guess talk about it a little bit further. Because one of the questions in assignment 2 is to characterize signals using certain terms, right? So I'll do that today. Then we will do another question on Fourier series as an example. And then I think we'll probably do one question on Laplace, okay? And that will sort of align with the second assignment. There's another question in the assignment, one related to sampling. And that is something we went through on lecture 6, right? Yeah. Lecture 6, we did some stuff on lecture 7, right? So lecture 7, we did some stuff on sampling and all of the terms you will pretty much find in that lecture, right? Related to undersampling, oversampling, and the questions around that. Okay, as usual, if anyone has any questions on that, they could feel free to reach out to me. But we'll go through the assignment in some more detail during this class. So that's what we're going to do this class. We're just going to cover some theory to ensure that you'll be okay in completing the second assignment, right? And when you all finish that assignment, that will be it in terms of the coursework. Okay, so for the coursework, we had 4 elements, right? So we had assignment 1, and then we had a midterm exam, we had the lab, and now we're going to have assignment 2. Right, so that's going to count as the or towards the coursework part of your grade, and then the final exam will be the remaining 50%. Okay, so that's what we're going to do today. Next week, or starting next week, we're going to do some revision, right? So the idea is to do 2 classes of revision to prepare you for the final exam. Okay, so the topics that will be coming in the final exam will include the signals and signal manipulation. So that topic we've been doing quite a bit of examples since the beginning of the term, right? That is where you have a signal and then you have to derive the equation for the signal. And after that, then you do some transformations on the signal, right? So, you time shift, time scaling, amplitude scaling, etc. Right, and sketch that. So that's one question. There's going to be, well, the second question is going to be to, well, given a signal to determine certain characteristics of it, and that is along the lines of it being memoryless, causal, non-causal, linear, non-linear, time invariant, and stable, bounded input, bounded output. Okay, so we did part of or some of that you were assessed on in the midterm exam, and we will look at that again, right? Another question you all will have is one related to Z transforms. Okay. Another one will be related to Laplace, and then the last one will be on Fourier. Okay, so if you all want, you all could start having a look at that, looking at the examples we did in class. But next week, the class, we will be going through questions on those topics. And then the last week, we just try to reinforce that information, right? So we'll do revision for 2 classes. And I think if you all review the information and, understand it, you will be in a good position for the final exam.
So we never did for the for finals for this class yet.
Final, I didn't get any information from examinations unit just yet. So I'm hoping soon we will be. All I know is just the period of the final exams, which is from the 1st of May to the 15th, I think. So it's going to be somewhere in between there.
All right.
So please do attend the last classes, everyone. I know it's a long semester, and it's a couple of courses you are working on, but I think these last couple of classes will be beneficial in terms of solidifying your understanding of the topics that will come for the exam. All right, so let us begin. We'll go through the lecture today, which is to sort of cover some of the information related, or you'll have to do in the assignment, right? And then we talk a little bit more the assignment. Oh, and one announcement regarding embedded systems, right? So embedded systems also is well, like with all we are going to be doing the presentations and stuff, the demonstrations and presentations from next week. So tomorrow would be, in terms of scheduled classes, will be the last class that we'll be meeting. Okay, so I will be on campus from about 1. So anyone who wants to come in earlier to work on their projects can do that, right? And tomorrow I'll talk a little bit about your requirements for the demonstration, right? So we'll do the demonstration next week. And then on the last week, we'll do the presentations. And I'm thinking we could probably do the presentations online, right? So that way we can record it and it'd be easier to, for everyone to view it, etc. So we do the presentations online on last week and the demonstrations next week.
Recording in progress.
All right, so today we're going to go through some classifications of signals, right? So signals can be classified in different ways using different terminology, right? And some of the main ways we're going to look at classifying signals is by being either analog or digital, deterministic or random, even or odd, and then periodic or aperiodic. All right, so let's get into some of these right now. Okay, so first one is, and this is just to sort of formalize the definition, right? So a continuous time signal, right? So signals are data functions of continuous variables. So time is a continuous variable, generally regarded as continuous time signals, right? So most of the signals that some function of time. So in this one here, we have like velocity and time, right? Then if we have a sine wave, that's a function of time. So those are generally continuous time signals, right? Right, so they generally have a value for each of the different units, right, or intervals that they are between intervals, right? For the analysis of the continuous time signals, we use Laplace, and then you could also use Fourier to analyze continuous time signals. Right, so this is an example how continuous time signals look. The other one is discrete time signals. And these signals, they are functions of a discrete variable, right? So it could be different like sampling points, right? It could be different areas. And these variables are usually in the form of an integer value. Okay, so on the x-axis for discrete time signals, it's normally in term n, right? And on the y-axis is normally some function of n, right? So x of n. Some differences between discrete and continuous time signals, other than the n and t, is the brackets and how it shows, right? So for discrete time signals, it's usually a square bracket, and for the continuous time signals, it's normally a curved brackets. So that's how it's represented. These are some more examples of discrete time signals. So it's usually at specific points you have a value, not throughout the entire signal. The next one is a signal could be even, and an even signal has a symmetry with respect to the vertical axis. Right? So what's going to happen is the signal at time t less than 0, so this is time t less than 0, is an image of the signal for time t greater than 0, right? And usually what happens is, as I said, it's a symmetry with respect to the vertical axis. So this is the vertical axis here, the y-axis. And if you were to mirror that, you would get, if you were to mirror what's on the positive side, right, you will get what is on the negative side. So this type of signal is considered an even signal, right? So mathematically, for continuous times even signal, x of t is equal to x of minus t, right? Remember the x of minus t, that function is a time reversal, right? So if you do a time reversal, it's going to be a mirror image on the vertical axis. Right. In terms of a discrete time signal, it would be represented like this, right? So x of n is equal to x of minus n. Other examples of even signals are these, and you notice the same thing here, right? So it's going to be a mirror image on the y-axis, right? So this shape is on the positive side is equal to the mirror image on that side, right? Right, similar to this one, you have one shape here, and if it's a mirror image on the y-axis, you're going to get this value here. And even this signal, right? So it's a little more complex, but if you look at it carefully, if we do a mirror image on the y-axis, what is on the positive end is going to be equal to the negative end. So all these signals are considered even signals, right? Now, the other side of that is odd signals. So odd signals it also has symmetry, but the symmetry for odd signals is with respect to the origin, right? So the origin is this point here, right? But another way of looking at it is this second point, right? So the portion of positive times can be flipped with respect to the vertical axis and then with respect to the horizontal axis, right? So these are the positive times here, okay? So what we're going to do is first we're going to flip it with respect to the vertical axis. So if you flip this, it's going to look like this, right? Then this, then this, and then this, right? So that's the first flip. And then the second flip is now with respect to the horizontal axis. So you're going to flip what I drew there in blue, and you're going to get the final waveform, right? So that's the second flip. And the result would be the signal at the negative time, right? So this signal is odd, and mathematically x of t is equal to minus x of minus t for continuous time signals. And then you have x of n being equal to minus x of minus n. Right, so that's an odd signal. And these are some other odd signals here, right? Examples of it. So if you look at another continuous time one, right? So if we flip this first on the vertical axis, you're going to get this value here, this signal here. And then if you flip that on the horizontal axis, you're going to get this shape there, right? So this signal is odd. And just how we can have an odd continuous time signal, we can also have an odd discrete time signal, right? So if you look at discrete time signal, this one here, and we flip it first on the vertical axis, you'll get the lines like this, right? So that's the vertical one. And then if you flip it on the horizontal one, you're going to get the final points there. So that's an odd signal, right? So you have continuous time, discrete time. Then we look at even signals, and then we have odd signals. Okay. The next one to look at is that of periodic signals. And a periodic signal is a signal that repeats itself after some time, right? And that time period is called t. Okay, so if you look at this signal here with these square waves, it is repeating itself every 2 seconds, right? So at -2 to 0, this is a shape. 2 seconds later, you have the same shape, right? And 2 seconds after that, you have the same shape. And the signal is going to continue. Well, it's continuing basically, right? So that is a periodic signal, a signal that repeats itself after some time. And many times in our in mathematics and calculations, we look at periodic signal, right? So the sine wave, the cosine waves, etc. It repeats itself after some time. The other side to that is that, this is an example of a periodic signal. Okay, so you see this this sawtooth shaped wave here, signal here, right? So it has this, right, time t, right? It does this, and another time t, it has the same shape, and time t, same shape, right? So this is a periodic signal also, right? Periodic signals could also be discrete time signals, right? And we see it looking at this particular signal. So you have 1, 2, 3, 4. No, we're going to start from here. 1, 2, 3, 4, right? And 1, 2, 3, 4, right? So it keeps repeating itself after the specific time. Then the other side of it is we have aperiodic signals, and basically an aperiodic signal is a signal that is not periodic, so it doesn't repeat itself after a specific amount of time. Now, we did talk about the analysis of aperiodic signals a little bit when we were doing a Fourier transform, right? Remember all the math when it came to dealing with the Fourier equations, it was based on signals being periodic. And what they did, because signals from some systems are not periodic, they basically made the assumption that the period for those signals would be infinity, right? So it's basically an aperiodic signal with a period of infinity, right? So that's how they looked at those signals to apply Fourier transform, right? So that is the aperiodic signal, right? The next one to look at is the deterministic signal. And in a deterministic signal, right, there is no uncertainty of the magnitude of the signal within a given instant of time, and also it has a regular pattern. So what that means is, given any moment in time, right, you could determine what the value is for the signal, right? That's deterministic. So this is a sine wave like type system, and then this is a sawtooth type system, where for any moment in time you could determine what the values are. So this is a deterministic signals, right? And generally these signals, they can be modeled in some form or fashion by a mathematical equation. Right? And the opposite to that would be a random signal. Okay, so a random signal is characterized by uncertainty. So there's no sort of predicting its behavior, right? And because of that, you cannot characterize a signal by any sort of mathematical equation. The pattern is generally irregular, cannot be predicted in advance, right? So that's an example of this sort of signal here. Okay, although there are some ways, there's some math being done to add or allow some sort of predictability as it relates to random signals. And that has to do when you look at stochastic processes and stochastic mathematics, where they use probabilities based on a behavior to determine what it could be, right? But that's that's a more advanced level mathematics. But in for our case here, we just have to be able to identify how a signal looks in terms of it being random or deterministic, aperiodic or periodic, or even discrete or continuous, right? And those will be easy to identify. Right, so we did, as I said, we did go through this a bit in the first lecture, but I just wanted to give you all some more examples on that. Right, so that's the signals characterization. The next, what I want to do next is I want to do a question on Fourier transformation, right? So let's do that. Let's do that next. So if you look at this question here, the figure illustrates a simple system utilized for controlling the pressure in a chamber in an industrial plant, where x of t, right, the input x of t, right, is pressure, right? So this is input pressure, and y of t is the output pressure of the system. All the respective initial conditions for the system is 0. And you have to answer these following questions, right? So first, you will find a relationship for A of t in terms of x of t and y of t, right? So for that, you focus on the sum injunction, right? Remember, this is the sum injunction here. So you take that into consideration, as well as the signs in the sum injunction to develop that relationship. Next, using the input and output of the integrator block, this here is the integrator block, write an expression for y in terms of A, and based on those two expressions that you got for A and B, you will write an expression for the differential equation that describes the system output, right? So the output is y, so you're going to write a differential equation for that. After that, you will do the Fourier transform on the system differential equation, and then based on that Fourier transform output, you will find the system transfer function h of omega. Okay, and remember, the reason why we find h of omega is because of the passing a signal through a system. If it is you are able to determine the system's response to an impulse signal, if it is you do the convolution of that impulse signal with any input signal, you could predict the output of it, right? But we're not doing a convolution. We are going to transfer that into another domain. In this case, we're going to use the Fourier domain. And that's because the convolution is generally computationally expensive, and it's easier to do that calculation in the Fourier domain in this case. And once we find the solution in the Fourier domain, then we could do the inverse Fourier transform and get the output in the time domain. Right, so that's the system transfer function h of omega. Right, now after you do that, then given an input signal, so now we're going to find the response to the input signal, right? So this is the input signal, 6e to the minus 2t u of t. You will derive an expression for the output y of t, but to do that, you'll follow these steps. So first, find the Fourier transform of x of t. Then determine the output y of omega in the Fourier domain, right? So we've had h of omega in part E, right? So this part here, this is h of omega, right? So now we're going to get y by basically it would be h of omega, x of omega, and that output y of omega is not going to be in a format that we can directly convert or put back in the time domain. So first, what we'll do is perform partial fraction decomposition on that y of omega. And finally, we will find the inverse Fourier transform of that decomposed y of omega and get the time domain output y of t. Okay, so all these steps are listed there, right? And we just answer the question by going through the steps one at a time. Okay, so the first part of the question is based on the signs at the sum injunction, right? A relationship for A in terms of X and Y, right? So this is A here, the output of the summing junction, right? So the output is equal to the sum of the input. So what do we have going into the summing junction? First, we have going in is X of t, right? So A of t is equal to X of t, that's the first one. And then secondly, we have a feedback loop here from the output. So you're gonna have 5y of t, right? So this is again here on the output, so 5y of t, but the summing junction has a negative sign, so it's going to be minus 5y of t. Okay, so that's how we get the first relationship here. So A of t is equal to X of t minus 5y of t. Secondly, using the input and output of the integrator block. Okay, so let's shift now. This is the integrator block here. So input and output of the integrator block, write an expression for y of t in terms of A of t. So we have y of t, which is the output, is equal to the integral of A of t dt. Okay, so this is what you have here. And what we could do one time is we can find what A of t is, right? So to get A of t, we differentiate each side, right? With respect to dt. So on the left side, this is going to be dy t dt. That's how you're going to get this here. And if we differentiate the integral of A of t dt with respect to dt, you're just going to get A of t, right? So that's how you're going to get this here. Right, so that is parts A and B. Okay, in part C, using the expressions obtained from parts A and B, you have to write a differential equation that describes the system out, right? So for this one, what you can do is, just to make it a little more organized, you could add equation numbers to each one of the equations. So from part A, you call that equation 1, and from part B, this could be referred to as equation 2. And then you're going to substitute A of t from equation 2. So what you're going to say is, so from this equation 2, you're going to substitute what A of t is into equation 1. So A of t is equal to dy dt. You're going to take this, and you're basically going to put it here, right? And that will give you dy of t dt being equal to X of t minus 5 y of t, right? And that will be it for part C. Now, part D is you have to write an expression for the Fourier transform of the system differential equation given in part C above, right? So the system differential equation is dy of t dt minus X of t minus 5y of t, right? Actually, this is a good point to, right? So let me just bring this up, right? So I just want to do this part of the question showing you the formula sheet. Okay, so we will go through the, as I said, we will go through the formula sheet in some more detail, but as we're doing the question, I want to show you exactly how to apply it here, right? So we're doing a question on a Fourier transform, and then this one is based on a continuous time signal, right? So you're going to have two main sections for each one of the transforms. So for the Fourier transform continuous time signal, they are the properties of the Fourier transform, and then there are the transform pairs, right? So these are the ones for the continuous time signals. Just to remind you really quick, for the discrete time signals, it's capital omega, right? So you see here, this here is capital omega, right? So discrete time systems, they use capital omega, and for the continuous time, they will use, it's generally used the common omega, right? Okay, so in our question, let's pull back up the question. So in the question, we have to find the Fourier transform of the system differential equation. And this is the system differential equation here, right? dy of t dt is equal to x of t minus 5 y of t. So first, what you would do is you will, well, you can. I just want to show you how to use the sheet, right? So if we look at the properties of the Fourier transform, we see here that a signal x of t, the Fourier transform of that is x of omega, right? So these are these generalizations of the signals. So how we apply that in this case is we will look at this here, right? So x of t is going to give you x of omega, right? And y of t is going to give you y of omega, right? So 5y of t is going to give you 5y of omega. So that's how you get this this sort of transformation here, right? Now, the next one we have to deal with is dy of t dt. So let's see how we do this one. So for that, we are looking at this part of the sheet here, time differentiation, right? And you see the x of t dt, the transform of that is going to give you j omega x of omega, right? So if we apply that now to our question, we will get, right? We will get j omega y of omega, right? So, and that's how you get the full Fourier transform here using the sheets, right? So I just wanted to show you how you could, how the formula sheets are used to do transformation, right? But I mean, I know we've had quite a bit of practice on it. So for this particular transformation, you may not have to look at the sheet, but just in case you're having a look at the formula sheet, that is how you translate from the system differential equation to the any time domain to the Fourier domain. All right, that is that. Okay, now part E is to find the system transfer function h of omega. Remember, h of omega is equal to y of omega divided by x of omega. So firstly, what we'll do is we just put the Fourier equation we got from part D, right? So j omega y of omega plus x of omega 5y of omega, and then we put the similar terms on each side, right? So we take the 5y minus 5y and put it on the left hand side, and that's going to give you j of omega y of omega plus 5y of omega. That's equal to x of omega. You factorize out the y of omega on the left side. It's going to be y of omega into j omega plus 5, and that's equal to x of omega, right? So now to get h of omega, we are going to divide both sides first by x of omega, right? And that will give you y of omega on x of omega on this side. And if you divide both sides by j of omega plus 5, you're going to get 1 over j omega plus 5, right? So this is going to be equal to your h of omega. Right, so now that we have the system transfer function, next we are going to put an input signal into the system and find the output, right? The output y of t in the time domain. But we're going to use, okay, so first the input signal is x of t, and that's equal to 6e of minus 2t u of t, right? And we will do these steps here. So first, we're going to find the Fourier transform of the input. So the 6e of minus 2t u of t. Next, we will determine the output y of t, right? So when we get that x of omega, we will multiply that by the h of omega, right? And that'll give us the y of omega. The third thing is to perform the partial fraction decomposition on the y of omega. And then finally, on that decomposed value, we will find the inverse Fourier transform of the y of omega, and we will get the time domain output. All right. Okay, so first let us look at finding the Fourier transform of the input x of t, right? So again, x of t is equal to 6e of minus 2t u of t, right? And to get this transformation, we look at the tables. So let us have a look at the tables ourselves. So the table for this one, so this what we were looking at for the converting a system differential equation to the Fourier transform, we looked at the properties of Fourier transform section, right? For this particular one, we will look at common Fourier transform pairs. Okay, so that's the section you're looking at. And then this one in particular is the one for this, right? So remember, it was what? It was 6e of minus 2t u of t, right? So this is the one here that closely goes to that. And the transformation is, or the pair for that is 1 over j omega plus a. In this case, a is equal to 2. Right? So let us go back. Question. Right, good. So here, this, yeah, Miguel, question?
Yeah, okay. So from the formula sheet, right? On
Yeah.
this page here, I see you have this in a red box, right? The one below it is pretty much similar, just have a T in front of the E.
Right.
Wouldn't that T represent like the 6?
No. That t has to do with a time value of variable coming in. That 6 is just an integer value.
Okay.
Right. So you see how this x is a function of time. So if there's another time related variable in that input, then we would have looked at that particular entry.
Okay. All right.
Right. But that is a good question. Right. So this is the one we're looking at. Right. E of minus 80 u of t. Right. 6 is just an integer value on the outside. So that's why how I did this here is the x of omega is going to be equals to 6 multiplied by the 1 over j omega plus 2, right? So 6 multiplied by the e of minus 2t u of t, right? And that's going to give you 6 over j omega plus 2, right? Right. So that is the first part. Okay, so secondly, you have to determine the output y of omega in the Fourier domain. And y of omega is equal to h of omega by x of omega. H of omega, we have that value from part E, which is 1 over j omega plus 5. And the x of omega, we just sorted that, well, we just found that out, which is 6 over j omega plus 2. Okay, so our y of omega is going to be equal to 6 over j omega plus 5 multiplied by j omega plus 2. Right, so now, well, the next step after this really is to get the time domain output of y of t, right? But for us to directly use our tables to get the transformation of this is going to be a little complicated. So what we'll do is we'll do the partial fraction decomposition, right? So just that that's the next step. Any questions? So if I just want to explain why it is the next step. So this is our y of omega, 6 over j omega plus 5 by j omega plus 2. Right, and this can be broken down into a over j omega plus 5 plus b over j omega plus 2, right? So basically, you're going to be using this partial fraction term to decompose it, right? So essentially what we're going to have here is 6 over j omega plus 5 multiplied by j omega plus 2. That is going to be equal to a over j omega plus 5 plus b over j omega plus 2. The first step you're going to take in this is you're going to multiply both sides of the equation by j omega plus 5, j omega plus 2. On the left-hand side, this is totally going to cancel out, so you're going to be ended up with 6. On the right-hand side, the j omega 5 is going to be out, so it's going to be a multiplied by j omega plus 2, and then on the b term, the j omega plus 2 is going to be out, so it's going to be b multiplied by j omega plus 5. Right, so this essentially is the equation that we'll be working with. Right, so next, what we're going to do is we're going to eliminate one of the terms in order to find the other one. So first, let us eliminate a by substituting j omega b equals to minus 2. Right, so that's going to give you 6 being equal to a into minus 2 plus 2 plus b multiplied by minus 2 plus 5. So minus 2 plus 2 is 0. So we're going to eliminate a with that, right? And b is going to be multiplied by minus 2 plus 5, which gives you 3. So 6 is equal to 3b, and that will give you b being equal to 6 on 3, and that's equal to 2. So now we have what b is. Let us find a. So to find a, what we can do is we can eliminate b. Now, b is equal to 5, so to eliminate b, we need to make this term here 0. To do that, we need j omega to be minus 5. So that's what we're going to do. We will substitute j omega being equals to minus 5 to eliminate b. So it's going to be 6 being equal to a into minus 5 plus 2, right? Because it has a j omega term here, plus b into a minus 5 plus 5. Right? So that's 6 being equal to minus 5 plus 2 is minus 3. And then minus 5 plus 5 is 0. And that's going to eliminate b. And that's going to give you 6 being equals to minus 3a. And a will be equal to minus 6 over 3. And that will be equals to minus 2, right? So now that we have terms for a and b, we are going to substitute that back into the original sort of partial fraction format, right? So y of omega is equal to a over j omega plus 5, where a is minus 2, so that'll give you minus 2 on j omega plus 5, plus b over j omega plus 2, and b is 2, and that's equal to b over j omega plus 2. So when you do your partial fraction decomposition, right, this is what you will end up with, a term like this. Another thing I want to just point out here, when you're doing the elimination, now let's just say, for example, this was j omega plus 0.5, right, 0.5. Right? The simplest thing to do in a case like this is when you have to eliminate b, just substitute j omega b equals to minus 0.5, right? So whatever the value is that you're trying to get eliminate, you're going to substitute the negative of it that is in bracket, right? So this was positive 0.5. You substitute j omega equals to negative 0.5, and that will very easily set the value to 0 and eliminate it. Right? I've also found that when we're doing these equations, and especially if we're dealing with fractions, right? So let's just say this was 1/5, for example. It's a lot easier to do if you use the decimal format, right? So you replace the 1/5 with 0.2. Okay, that's just a little tip you can use also if you have decimals or fractions in there. All right, so now that we have, now that we have the equation that is decomposed, what we need to do is we will find the inverse Fourier transform of the y of omega to determine the time domain output y of t, right? So again, we will just take a look at this. This is the y of omega that we just found. And to find the time domain output, we will take terms one at a time, right? One at a time. So what we're looking at here, the first term is minus 2 over j omega plus 5, right? I'm just going to pull up the notes and formula sheets. Right, so what we had here, right? So we had minus 2 over j omega plus 5. And remember that is essentially okay, right. So you have minus 2 over j omega plus 5, right? And that is essentially minus 2 multiplied by 1 over j omega plus 5, right? So if you look at the 1 over j omega plus 5, that resembles this form here, right? Where a is equal to 5. And to get the time domain output of that is going to be e to the minus at u of t, right? And in this case, a is equal to 5. So that's going to give you e into minus 5 of t u of t, right? But we have to remember about this minus 2, right? So that's how you're going to get minus 2 e to the minus 5t u of t, right? And that's how you will get this value here, right? Minus 2 over j omega plus 5 is equal to minus 2 e to the minus 5t u of t, right? So that's the first term. If we look at the second term, which is 2 over j omega plus 2, right? So once again, that's going to be 2 over j omega plus 2, which is essentially 2 multiplied by 1 over j omega plus 2, right? And if you look at the tables, right? So you have here 1 over j omega plus a here, right? And that is the form closest to it, where a is equal to 2. And if you take the transform of that, you're going to get e to the minus 2t u of t, right? We go back, right? E to the minus 2t u of t, and we can't forget about the 2, right? So now that we have the 2 terms in the time domain, now we can put them together, and y of t is equal to minus 2 e to the minus 5t u of t plus 2 e to the minus 2t u of t, right? And here you could factorize out the 2u of t, and you could put this term first, right? Given that it's positive, you're going to get 2u of t into e to the minus 2t minus e to the minus 5t. This is the answer. Now, as I said before, right, if you leave the answer in this form, it is totally fine, right? You don't have to simplify it further, right? That's totally okay. Right. One thing I want to point out, though, is you need to be very careful when you are putting how you express the different forms, right? So for example, the time domain, it is always going to be a common, right? So common y and in brackets t, right? And when you're in the Fourier domain, it is going to be capital, right? So capital Y, for example, and then omega. So that's important. So you don't want to put something like, just say you were doing this part of the question. So when we had to do this part of the question, right? So when we did this part, you don't want to do common y omega, right, equals common x omega, because that's incorrect, right? It has to be a capital letter. All right, so just pay attention to that. All right. Any questions on the Fourier? If you all have any doubts, you just let me know, right? All right, so that is Fourier series, right? And I want to do one example also on Laplace. Right. So the next question I have here is a Laplace question. So this system is a simple model of a continuous time system where y of t is the output and x of t is the input, right? And for the system, we have to answer these questions. So again, based on the signs at the summing junction, write a relationship for E of t in terms of x and y, right? So this is E of t here, right? Using the input and output from the integrator block. So this is the integrator block again. Write an expression for y in terms of E. And then using these expressions, write an expression for the differential equation that describes the system output. Now, using that equation, you have to find the Laplace transform of it, then the system function, h of s, right? So again, remember Laplace, it's in terms of s. Fourier is in terms of omega, right? And then z transform, it's z. Okay, when you have that, then given an input signal x of t being equals to 2u of t, derive an expression for the output of y of t, and you will follow these steps. So first, find the Laplace transform of x of t, right? Then determine the output y of s in the Laplace domain. Thirdly, you will perform partial fraction decomposition on y of s, and then finally, find the inverse transform of y of s to obtain the time domain output. Right, so in terms of the steps, it is pretty similar in terms of what has to be done. You just have to pay attention to how you express it, right? So Laplace is expressed in terms of s, Fourier is in terms of omega, and also you have to use the proper properties and transformation tables to do the mapping, right? So just you have to pay attention to that. All right, okay. So first, let's look at write a relationship between E in terms of X and Y, right? So we have E as the output of the summing junction, and then we look at all the terms coming in. So coming into the summing junction, we have X of t, and then we have 0.5 Y of t, right? So that's this multiplied by this, but there's a negative sign also, right? So negative or minus 0.5 Y of t, right? So that's E. For part B, using the input and output of the integrator block, write an expression for y in terms of E. Okay, so y is equal to the integral of E of t dt, right? So in this time we have a term E of t as the input, right? And from here to get E of t, we differentiate both sides of this equation by respect to dt. So you're going to get dy of t dt is being equal to E of t, right? So you just make E of t the subject here. Right. And using the expressions from A and B before, you have to write an expression for the differential equation that describes the system output. So once again, for part A, you could just label that equation 1, and for part B, that expression, you could call that equation 2, right? And then what you're going to do is from equation 2, you're going to substitute E of t. So in equation 2, E of t is equal to dy of t dt. You're going to substitute that value into equation 1. So you're basically going to replace E of t with that. And that will give you dy of t dt being equals to x of t minus 1.5 y of t, right? And that here will be your differential equation that describes the system output. Right, so next we have to write the expression for the Laplace transform of that system differential equation, right? So this is the differential equation from part C, which is dy of t dt being equal to x of t minus 1.5 y of t, right? So let's look at the formula sheets here, how we could use that. All right, so first thing is we will move to the Laplace side of it, right? So, okay, so we have here, and again, you're going to have two different tables for Laplace, right? So you're going to have the common Laplace transform pairs, right? But in this case, we will be looking at the properties of the Laplace transform, right? And again, we see here, right, at the very top, x of t, right, in time domain is going to give you x of s, right? Capital X of s. Right, so that is if we apply that to, right, if we apply that here, we see x of t going to capital X of s, and 1.5 y of t will give you 1.5 capital Y of s, right? So that's that part. Next thing we're going to look for is this dy of t dt. Right, so let's go back to the tables here. Right. So, okay, so here if we go down, yeah, if we scroll, right, yeah, so this is it here, right? So we have the x of t dt, right? And that goes to s capital X of s, right? So that's the differentiation, and that's in table what you're looking for, right? Okay, so now we are going to apply that here, right? And we see here now, the dy of t dt, and that goes to the s capital Y of s, right? So again, right, I know we've been doing the examples with it, and you all are familiar with moving from the differential equation to the Laplace transform, but I just want you to see how that transformation really is done when you reference the tables, right? Okay. After we do that, then we have to find the system function h of s, right? So again, h of s is equal to y of s over x of s. Okay, so then we write our system function here. That's system function, or Laplace transform of the differential equation. S of y of s is equal to x of s minus 1.5 y of s, right? You move the common terms to each side, so you're going to get s y of s plus 1.5 y of s, and that's going to be equal to x of s. Then you factorize out the y of s, and we're going to give you y of s into s plus 1.5, and that's equal to x of s. So to get h of s, okay, first you divide both sides by x of s, and then you divide both sides by s plus 1.5, and that will give you y of s over x of s being equal to 1 over s plus 1.5. Right, so that here is your system function, right here, 1 over s plus 1.5. Okay, so now that we have that, then we're going to input a signal into the system and try to get the response, right? So the signal that's put into the system is 2u of t, and you have to follow these steps to get the output in the time domain. First, the Laplace transform of x of t, then to determine the output y of s in the Laplace domain. Thirdly, again, you will do partial fraction decomposition of YFS. And then finally, based on that output there, you would find the inverse Laplace transform of YFS to obtain the time domain output Y of t. So first, we are going to find the Laplace transform of x of t, right? So x of t we have here being equals to 2u of t. And to do this, we could look at our Laplace transformation table. So let's look at the transformation table here. Right. So the transformation table is this was the properties table we were looking at before. So the transformation table is this one, right? So the transform pairs, right? And what we were looking at was what? 2u of t, right? So that's 2 multiplied by u of t, right? And for u of t, the transform of that is 1 over s. Okay, 1 over s. So back to our question. Right. So x of s is going to be equals to 2 multiplied by 1 over s, which is 2 over s. Right? So that's your Laplace transform of x of t. Next, you need to determine the output y of s in the Laplace domain. Remember, y of s is equal to h of s, x of s, right? We got x of s just now, which is 2 over s, right? And then h of s we got in part E. H of s is 1 over s plus 1.5. Right, so y of s is equal to 1 over s plus 1.5 multiplied by 2 over s, and that is going to give you 2 over s into s plus 1.5. Right, so that here is your output y of s in the Laplace domain. All right, and next you have to perform a partial fraction decomposition on y of s. Right, so this is essentially a term in s multiplied by term s plus 1.5, right? So we use the same terms here, a over ax plus b, the same general term. And you're going to say y of s is equal to a over s plus b over s plus 1.5, right? Next, you're going to equate that. So 2 over s into s plus 1.5 is equal to a over s plus b over s plus 1.5. To start solving, you will first multiply both sides of the equation by both sides of the equation by s into s plus 1.5. All right, so this is going to get rid of the entire denominator on the left-hand side. So that's going to give you 2, right? On the right-hand side for the a term, the s is going to be taken off. So it's going to be a into s plus 1.5. And for the b term, s plus 1.5 is going to be taken off. So it's going to be b multiplied by s. Right, that's going to give you finally 2 equals a into s plus 1.5 plus b multiplied by s. Right. So now that we have that, next thing we want to do is we want to solve for a and b. Okay, so we will eliminate the terms one at a time. So first, let's eliminate a. Right. So remember what I was saying before, right? So we have here a fraction. We have a into s plus 1.5, right? So this 1.5 is fraction. So the best way to deal with this is to just substitute s equal to minus 1.5, right? So just negative this value, right? And I'll give you 2 equals a into minus 1.5 plus 1.5 plus b, and the term here is only s minus 1.5. That'll give you 2 equals to a 0 by a, you're going to eliminate a, plus b into minus 1.5, and that's 2 is equal to minus 1.5 b, which gives you b as negative 1.33. Right? So that is the value of b. So now that we have that, let's get a value for A. Okay, so to get A, we will eliminate B, right? And it is B is going to be multiplied by S, so we substitute S as 0 to eliminate B. So A is equal 2 is equal to A into 0 plus 1.5, and B is eliminated. So A is equal to 2 divided by 1.5 is going to give you plus 1.33. Right, so now we have the values for A and B, right? We could substitute that to give you the YFS. So YFS is equal to 1.33 over S minus 1.33 over S plus 1.5. Okay, and that will be the end of your part 3 here, which is the partial fraction decomposition of YS. Okay, and the last part to the question is to find the inverse Laplace transform of YFS to obtain the time domain output Y of t. Once again, what we have here is we have YFS in 2 terms, right? So we have the 1.33 over S, and the second term is 1.33 over S plus 1.5. All right, so what we'll do is we'll take each term separately, right? So to do that, let us look. Okay, so the first term is 1.33 over S. Okay, and let's have a look at the table. Right, so 1.33 over S, which is essentially 1.33 multiplied by 1 over S, right? So 1 over S, right? This transform back into the time domain is going to give you U of t. Okay, so that's how we're going to get, that's how we're going to get 1.33 U of t for the first term, right? And the second term, we have 1.33 divided by S plus 1.5, right? And this is 1.33 multiplied by 1 over S plus 1.5. So to transform that, let's look at the table, right? 1.33 multiplied by 1 over S plus 1.5, right? We have here this 1 over S plus A, where A is equal to 1.5. And if we transform that into the time domain, that's going to give you E of minus AT U of t, where A is 1.5, right? So that's E of minus 1.5 T U of t. And if we look at that here, right? So if we look at that here now, that will result would be 1.33 E of minus 1.5 T U of t. So this is the second term. So we put it all together and we're going to get 1.33 U of t minus 1.33 E of minus 1.5 T U of t. Okay, and we could simplify this even more. You know, we take the 1.33 U of t out, and that will give you 1.33 U of t into 1 minus E minus 1.5 T U of t. Okay, so this is the simplified answer here. But I said before, right? If you leave your answer in this format, it is totally fine. Right, so no need to you know, simplify it further. If it is you want to, no problem with that. All right, and that's your solution there for the Laplace. All right, how everybody feeling about the Laplace and the Fourier? Feeling comfortable enough with it?
Yes, sir.
Yeah.
Okay, perfect. If it is, you know, if it is your, you know, have any doubts, just let me know. We'll do some more questions, and we will be doing some more questions to prepare you. All right.
Recording
Okay,
stopped.
so that's it for the questions that I have to show for you today, right? Next thing I want to do, as I said in beginner classes, I just want to go through the assignment with you, right? I want to go through the assignment with you, and then I want to just go through the formula sheet from the beginning, so you are familiar with that. Okay, and then we will, yeah, that will be it for today's class. right? And then next week we'll do the revisions. So now it's 6:15. Let's take a 10-minute break, right? We come back at 6:25. We do the attendance and we will talk some more about it. Okay, so see you all in 10 minutes. Table in terms of bounded input, bounded output, and then you're going to have a question given a signal to determine the equation of the signal in terms of ramp and unit step functions, and then apply some transformations to them, right? So like time shifting, times scaling, things like that. So we'll get into those questions from next week. Right. Today, what I did is I went through some questions to sort of prepare you, well, for the assignment, right? Let's just have a look at the assignment. I will put it up here. Right, so this is assignment. Yeah, this is assignment 2. Okay, so you have 3 questions. The first question is given some signals, right? So you're going to be given some signals here. And given these signals, you have to classify them using these terms. So you have to state whether they are continuous time, discrete time, even or odd, periodic, aperiodic, deterministic, or random. Now, each one of these signals, it may have multiple characteristics, right? So you could use one or more term to classify them, right? And it's also possible that there may be a signal here that, one term is not used at all, right? So don't feel the need, you have to use all the terms. So this is what is, part A, this is the first signal, what it looks like, right? Now, what I would tell you is use the marking scheme as a guide, right? In terms of how many terms you should use at least to describe the signal. Okay, so have a look at the signal, right? And then use these terms to classify the signal. Right. Thanks, Neil. I understand. Yeah. All right. So you have this first signal here, A, and you have another one, B, you have a third one, C, and a last one, right? If you have any questions on the, on these things, you could let me know, right? But basically, look at the signal, and then based on how the signal looks, based on the information you see there, classify them using different terms, right? As a hint, I say, look at the marks awarded for each part, and then use that to sort of estimate on how much signals, or how much terms at least you should use. All right, so that's the first question. The second one is related to sampling, right? And we did this a couple lectures ago. I think it was lectures. Get the right lecture here for you. It was lecture 7, right? So in lecture 7, we did sampling. Okay, and so for the first question, you have to determine what is the minimum sampling frequency, okay, given this signal with a frequency of 3000 hertz, right? The next one is you have to basically identify what is aliasing, then talk about what is oversampling, state an advantage and disadvantage of oversampling. And then finally, look at undersampling. So what is undersampling? And then state an advantage and a disadvantage of it. Okay, so those answers will be as part of your notes also, right? That note there. And then finally, question 3 is one based on a Fourier transform. So we have a system, and then based on this system here, you have to answer some questions, right? So similar to the ones we've been doing. Okay, what is the relationship between A and X and Y? Relationship between Y in terms of A. Then we'll find the system output, find the Fourier transform, find the system function, and then given an input signal, perform these steps, and then eventually find the time domain output Y of t. Okay, I also put some of the relative information you need. So I put the Fourier transform pairs and then the properties in this question, right? So this question, similar to the first, this assignment, similar to the first one, you can type it out, right, on in a document and upload that, or if you want, you could write it on paper, and then you could capture an image of the answers and then upload it, right? So anyone that is comfortable to you all, you could feel free to do that. All right, yeah, so that's the assignment. Any questions on that? Everybody clear? If you have any questions, you will let me know, right? Okay, the next thing I want to show you is the formula sheet. Is that showing now? Yeah. Okay. So I said this, as I said, this is the notes and formula sheet information, right? In the exam, you will have this information. So the first one is related to LTI systems. Okay, and these are the properties that you have to kind of prove whether your system is linear, time invariant, or stable. Right. So remember, we did this particular property in the midterm exam, right? So for linear systems, the superposition property has to be satisfied, right? And this is the superposition property here. For time invariant, this is what has to be satisfied, or you have to show this. And then for stable systems, this is what you basically defines if a system is bounded input, bounded output. Right now, remember, this is a general sort of formula sheet. So you have to apply it to your specific situation or specific question, right? And what I mean by that is, if you look at this the superposition property here, you notice it is in T, right? In terms of T. Now, if it is you have a question that is a discrete time question, you have to modify it for that, right? So instead of y of t being t of x of t, you will put y of n being equal to tx of n, right? So it's just to modify it based on the question it is. Right, so for example, the stable one is it's in the format of a discrete time one. Okay, so you just adjust based on what you need to, what you're required to the question, based on the question. Right, so that's the one for linear time systems. You have this information. And then there is the partial fraction table that we've been looking at when we do the partial fraction decomposition. Okay, so the entire table is in there, but based on the questions, you all know which one, or be familiar with which ones we generally use, right? That's the first page. The second page is you're gonna have some Laplace transform pairs, right? So this is gonna have the Laplace transform pairs, and this is basically looking at something in the time domain and what is the Laplace domain representation of it. Right? So for example, u of t in the time domain is going to give you 1 over s in the Laplace domain. Right, so that's one we generally use. And another one we've seen quite a bit is this one here, 1 over s plus a, and that gives you the form e of minus at u of t. Right, so this is the first table of the Laplace transform pairs. The second table is that showing the properties of the Laplace transform. Right, and generally ones we reference here this one where we go from x of t to x of s, right? So again, this is a generalized table. So if you have y of t, that will go to capital Y of s, right? And then we have the differentiation. So the x of t dt is sx of s, right? So if you had the y of t dt, that's going to give you s y of s, right? Right, so that is Laplace. After Laplace, we have these Z transform pairs. Okay, so this here is for the discrete time systems, right? And this is what we've been using, 1 over 1 minus z to the minus 1. That in the time domain, it is the U of n, right? Right, and then on the properties, you have here also x of n transform is x of z, capital X of z. And similarly, y of n would give you capital Y of z. Right, and yeah. Okay, so that is z and Laplace. After that, you have the Fourier transform here, right? So one thing to note about the Fourier transform has two different types of categories of tables, right? So there's the continuous time signals and then there are the discrete time signals, right? Remember, one way of differentiating between them is the omega term. For continuous time signals, it is common omega, and for the discrete time signals, I'll just scroll it real quick, is the capital omega, right? So that is one way of distinguishing between them also. Right, so we see here, right, so some we saw already, E3 minus AT U of t, and that in the Fourier transform is 1 over j omega plus A, right? If we go down, so same thing, you have the transform pairs and then you have the properties. So for the properties, right, we see here x of t, x of omega, and then we see here the time differentiation, the x of t dt giving you j omega x of omega, right? Again, if it was y, if it was dy of t dt, that will give you j omega y of omega. Right, so that's it for the continuous time. And then you would see here afterwards, the last couple tables are related to Fourier transform for discrete time signals, right? Discrete time signals. Right, so again, you have the common transform pairs, and finally, you're going to have properties of the discrete time signal. Okay, right. So please do take some time to look through and familiarize yourself with the tables, right? Just so on the day you could easily identify which ones you need to use. Even though based on the amount of questions you do, you might sort of memorize some of the transformations. It is good still to double check with the tables, right? In case you make an error. So that's generally happens when you review things frequently enough. You kind of memorize certain aspects of it, but still, good to familiarize yourself with tables so that you can double check on what is happening there. Right, okay, so we have assignment 2. Yes, so assignment 2, you all could upload that on Canvas, and when you all submit assignment 2, that will be it in terms of the coursework element for this course. Right, so you all did 2 assignments. Assignment 1, this is assignment 2. You did the midterm exam, you did the lab activity, right? So that's 4 elements to it, and then you're going to have the final exam to the end, right? So I think with the last 2 classes we have coming up, if you all come in and we do enough revision with the question, and you all review that thoroughly and understand it, you will be in pretty good shape for the final exam next month. Okay, and that will be good, right? Also, just an announcement for embedded systems persons. Tomorrow I will be on campus from 1. So if it is you all want to come in at that time, I will be there. If you all come in earlier, you can always check to see if Krishna is there and he could let you into the lab, right? Because tomorrow will be the last scheduled class for working on the project. Now, if it is you all still have things to do, you could come during the week, but you'll have to just sort of coordinate Krishna to get access into the lab, right? So tomorrow is not the final date to work on your projects, but it is the last class before the demonstration. So next week we are going to do demonstrations for embedded systems, and then the final week of the term, the final class for embedded systems, we are going to do the presentation. It'll be online. So tomorrow I'll talk to you all a bit about the demonstrations, just probably reiterate some of the things that you have to focus on for it next week, right? Right, so that's embedded systems. And yeah, that's it.
So, question, so for tomorrow, even if you finish your project, you gotta come to class for embedded, right?
Well, it is a class, and what I want to do though is I want to make sure you all, meaning the projects, that you all have everything sort of in order and you all have like all the required functionality in place for the demonstration. So depending on how far along you reach, you may not have to stay very long at all, right? But I just want to make sure everyone is progressing well. I don't want persons to come in on demonstration, they may have probably not thoroughly looked at demonstrating certain features, etc.
Okay.
Right. Good. Thanks, Keller. That's a good question. Right. Any other questions? No? All right. Okay, so if there are no more questions, you all work on the assignment, second assignment. If you have any questions, while you're doing it, always feel free to reach out to me. Or if I'm seeing you before, we could have a discussion before, right? Okay, so if that's it, guys, well, I will see you all next week, Monday. I will start the revision for the final exam. All right, so have a good night, everyone. Thank you, and see you all next time.